concern about a lost neutral between the meter and the main panel is valid. Without a grounded conductor, meaning neutral, return path between the meter and the main panel, a lost neutral could result in an open neutral condition. This situation could lead to overvoltages and potential damage to electrical equipment. Section 310.4 of the National Electrical Code requires that the grounding electrode conductor, which is the GEC, be connected to the service equipment, which is typically the main panel, and extended to the meter enclosure. Bringing the GEC only into the meter socket may be considered a violation of this code. It's understandable that the power company requires the GEC to be in the meter socket for proper grounding purposes. However, given the unique situation of the service entrance conductors being piped underground, there may be an alternative solution. One possible solution would be to install a ground rod near the meter socket and connect the GEC to the ground rod, as well as to the meter enclosure. This would provide a ground return path in case of a lost neutral. It is recommended to discuss this alternative solution with the power company. Explain the concerns and the potential hazards of a lost neutral condition. It may be possible to convince them to allow the GEC to be connected to a ground rod near the meter socket instead of directly into the meter socket. While bringing the GEC only into the meter socket may be a technical violation of the National Electrical Code, the safety concerns of a lost neutral must be addressed. By exploring alternative grounding solutions, such as a nearby ground rod, both compliance with code requirements and ensuring the safety of the electrical system can be achieved. When dealing with electrical installations, grounding is a critical safety measure. It provides a low impedance path for fault currents to return to the source, allowing overcurrent protective devices like circuit breakers or fuses to quickly trip and de-energize the circuit. This protects people and equipment from electrical shock and damage. The grounding electrode conductor, or GEC, is the conductor that connects the service equipment to the grounding electrode system. The grounding electrode system typically consists of items like ground rods, ground plates, or the metal underground water pipe. The size of the GEC is determined by the size of the service entrance conductors, as specified in the National Electrical Code, specifically in Table 250.66. The GEC must be securely connected to both the service equipment and the grounding electrode. In a typical service installation, the GEC is connected to the neutral bus in the main panel, which is bonded to the metal enclosure of the panel. This creates a single-point ground, ensuring that all non-current carrying metal parts of the electrical system are at the same potential as the earth. When the service entrance conductors are run underground, it's especially important to ensure that the grounding system is properly installed and maintained. Underground conductors are more susceptible to damage from moisture, corrosion, and physical stress. A break in the neutral conductor can create a dangerous situation where the voltage on different circuits in the building can become unbalanced. This can damage sensitive electronic equipment and pose a safety hazard to anyone who comes into contact with the electrical system. If there is concern about the integrity of the neutral conductor, additional grounding electrodes can be installed to provide redundant grounding paths. This can help to minimize the risk of a lost neutral condition. It is also important to regularly inspect the grounding system to ensure that all connections are tight and free from corrosion. If any problems are found, they should be corrected immediately. The National Electrical Code provides detailed requirements for the installation and maintenance of grounding systems. It is important to be familiar with these requirements and to follow them carefully. The code is updated every 3 years, so it's important to stay up to date with the latest changes. In addition to the NEC requirements, local codes and regulations may also apply. It is important to check with the local authorities to ensure that all electrical work is in compliance with all applicable codes and regulations. When working on electrical systems, it is always important to take precautions to protect yourself from electrical shock. Always energize the circuit before working on it, and use appropriate personal protective equipment such as rubber gloves and safety glasses. If unsure about how to perform a particular task, consult with a qualified electrician. Grounding is an essential part of electrical safety. By following the requirements of the National Electrical Code and taking appropriate precautions, it is possible to minimize the risk of electrical shock and damage to equipment. If you encounter a situation where the power company requires the GEC to be connected to the meter socket but you are concerned about a loss-neutral condition, there are several options to consider. Firstly, carefully inspect the existing grounding system to ensure that it is properly installed and maintained. Check all connections to make sure they are tight and free from corrosion. If the grounding system is not up to par, correct any deficiencies before proceeding. Secondly, consider installing a supplemental grounding electrode near the meter socket. This could be a ground rod, ground plate, or other approved grounding electrode. Connect the GEC to the supplemental grounding electrode in addition to the meter socket. This will provide a redundant grounding path in case of a loss neutral. Thirdly, discuss the situation with the power company. Explain the concerns about a loss neutral and the potential hazards it could create. Ask if they would be willing to allow the GEC to be connected to a ground rod near the meter socket instead of directly into the meter socket. It is possible that they may be willing to make an exception in this case, especially if the safety concerns are clearly explained. Fourthly, consult with a qualified electrical engineer. An engineer can review the specific installation and provide recommendations on the best way to address the grounding concerns. They can also perform calculations to ensure that the grounding system is adequate to handle any potential fault currents. Fifthly, document all decisions and actions taken. Keep a record of all discussions with the power company, the recommendations of the electrical engineer, and any changes made to the grounding system. This will be helpful if there are any questions or concerns in the future. Remember that electrical work can be dangerous. If unsure about how to proceed, always consult with a qualified electrician. Incorrectly installed electrical systems can create safety hazards and damage equipment. Grounding is a critical safety feature in electrical systems. It protects people and equipment from electrical shock and damage. By following the requirements of the National Electrical Code and taking appropriate precautions, it is possible to ensure that electrical systems are properly grounded and safe to operate. In the situation described, the local power company's requirement to bring the grounding electrode conductor GEC into the meter socket presents a potential conflict with the National Electrical Code (NEC) and raises concerns about a loss-neutral condition. It's crucial to address these concerns to ensure the safety and reliability of the electrical system. Firstly, let's delve deeper into the NEC requirements. Section 250.24c of the NEC generally mandates that the neutral conductor be grounded to the service equipment. This means that the connection between the neutral conductor and the grounding electrode system, which includes the GEC, should ideally occur at the main service disconnect. This arrangement ensures a lower impedance path for fault currents and helps to stabilize the voltage during normal operation. Secondly, the concern about a loss neutral is valid and should not be taken lightly. If the neutral conductor becomes disconnected between the meter socket and the main service disconnect, it can lead to an imbalance in voltage on the various branch circuits within the building. This imbalance can cause appliances and equipment to operate at voltages outside their designed range, potentially leading to damage or failure. In severe cases, it can also create a shock hazard. Thirdly, the power company's requirement to bring the GEC into the meter socket likely stems from their desire to ensure proper grounding of the meter enclosure itself. A properly grounded meter enclosure helps to prevent voltage from appearing on the enclosure, which could pose a hazard to meter readers or anyone who comes into contact with it. However, this requirement should not compromise the overall safety and grounding effectiveness of the electrical system. Fourthly, given the existing underground service entrance conductors and the lack of space for a disconnect next to the meter, finding a compliant and safe solution requires careful consideration. One approach is to explore the possibility of installing a remote service disconnect. This would involve locating the main service disconnect at a more accessible location closer to the load and running the service entrance conductors from the meter socket to the disconnect. This arrangement would allow for the GEC to be properly connected to the neutral bus at the service disconnect in accordance with NEC requirements. Fifthly, if installing a remote service disconnect is not feasible, another option is to install a supplemental grounding electrode at the meter socket. This could involve driving a ground rod or installing a ground plate near the meter and connecting it to the meter enclosure with a separate grounding conductor. This supplemental grounding electrode would provide an additional path for fault currents to return to the source, helping to mitigate the risks associated with a lost neutral. However, it's important to note that this supplemental grounding electrode should not be used as the primary grounding electrode for the service. The primary GEC should still be connected to the neutral bus at the main service disconnect if possible. Sixthly, regardless of the chosen solution, it's crucial to have a thorough discussion with the power company. Explain the concerns about a lost neutral and the potential code violations associated with bringing the GEC only into the meter socket. Present the proposed alternative solution, whether it's installing a remote service disconnect or adding a supplemental grounding electrode, and explain how it addresses the safety concerns. Be prepared to provide documentation and diagrams to support the proposal. The power company may have specific requirements or preferences, and it's important to work collaboratively to find a solution that meets their needs while also ensuring compliance with the NEC and prioritizing safety. Seventhly, when implementing any changes to the grounding system, it's essential to follow all applicable codes and regulations. Consult with a qualified electrical inspector to ensure that the work is performed in a safe and compliant manner. Obtain all necessary permits and approvals before starting any work. Properly document all changes to the electrical system, including the location of grounding electrodes, the size and type of grounding conductors, and the methods of connection. This documentation will be valuable for future maintenance and troubleshooting. Finally, remember that electrical work can be dangerous, and it's always best to err on the side of caution. If unsure about any aspect of the work, consult with a qualified electrician or electrical engineer. Never attempt to perform electrical work unless properly trained and equipped. By carefully considering the NEC requirements, the potential hazards of a lost neutral, and the power company's requirements, it's possible to find a solution that ensures the safety and reliability of the electrical system. Communication, collaboration, and adherence to code are key to achieving a successful outcome. Furthermore, let's consider the practical steps involved in installing a ground rod as a supplemental grounding electrode, as this seems to be a viable solution given the constraints. Firstly, select an appropriate location for the ground rod. It should be as close as possible to the meter socket, ideally within a few feet. Ensure that the location is free from underground utilities, such as gas lines, water pipes, and electrical cables. Call the local utility locating service to mark the location of any underground utilities before digging. Secondly, choose a ground rod that meets the requirements of the NEC. Typically, a ground rod should be at least 8 feet long and made of copper, copper-clad steel, or stainless steel. The diameter of the rod should be at least 5/8 inch for copper and copper-clad steel, or 1/2 inch for stainless steel. Thirdly, drive the ground rod into the earth until it is fully buried, except for a few inches at the top for making the connection. A ground rod driver can be used to make this task easier. If it is not possible to drive the ground rod to its full length due to rocky soil, it can be buried at an angle not exceeding 45 degrees from vertical, or it can be buried in a trench at least 30 inches deep. Fourthly, connect the grounding electrode conductor, GEC, to the ground rod using an approved connector. The connector should be listed for direct burial and should be compatible with the materials of the GEC and the ground rod. Ensure that the connection is tight and corrosion resistant. Fifthly, run the GEC from the ground rod to the meter enclosure. The GEC should be sized according to Table 250.66 of the NEC, based on the size of the service entrance conductors. The GEC should be run in a straight line as much as possible, and it should be protected from physical damage. Sixthly, connect the GEC to the meter enclosure using an approved connector. The connector should be listed for grounding and should be compatible with the materials of the GEC and the meter enclosure. Ensure that the connection is tight and corrosion resistant. Seventhly, inspect the completed installation to ensure that it meets all applicable code requirements. Check that the ground rod is properly installed, that the GEC is properly sized and connected, and that all connections are tight and corrosion resistant. Eighthly, document the installation for future reference. Record the location of the ground rod, the size and type of GEC, the type of connectors used, and the date of installation. This information will be helpful for future maintenance and troubleshooting. By following these practical steps, a supplemental grounding electrode can be installed at the meter socket to provide an additional path for fault currents and to mitigate the risks associated with a lost neutral. Remember to consult with a qualified electrician or electrical engineer if there are any questions or concerns about the installation. And above all, prioritize safety when working with electricity. Always de-energize the circuit before working on it, and use appropriate personal protective equipment. The NEC Article 250 provides comprehensive guidelines on grounding and bonding, and compliance with these requirements is paramount for ensuring electrical safety. The goal is to create a low impedance path for fault currents to return to the source, which allows overcurrent protection devices to quickly trip and clear the fault. This minimizes the risk of electrical shock and fire. When dealing with existing installations, it's essential to assess the existing grounding system to identify any deficiencies. This includes checking the size and condition of the grounding electrode conductor, the grounding electrodes, and the bonding connections. If any deficiencies are found, they should be corrected promptly. It's also important to consider the impact of any modifications or additions to the electrical system on the existing grounding system. Any changes should be carefully evaluated to ensure that they do not compromise the effectiveness of the grounding system. In some cases, it may be necessary to upgrade the grounding system to accommodate the increased load or to improve its performance. The power company's requirement to have the GEC connected at the meter socket highlights the importance of grounding the meter enclosure. This helps to prevent voltage from appearing on the enclosure, which could pose a hazard to meter readers or other personnel who come into contact with it. However, as discussed earlier, this requirement should not compromise the overall effectiveness of the grounding system. It's crucial to find a solution that meets the power company's requirements while also ensuring compliance with the NEC and prioritizing safety. In addition to ground rods, other types of grounding electrodes can be used, such as ground plates and underground metal water pipes. The choice of grounding electrode depends on the soil conditions and the availability of suitable electrodes. Ground plates are typically used in areas with high soil resistivity, while underground metal water pipes can be used as grounding electrodes if they meet certain requirements. When using an underground metal water pipe as a grounding electrode, it's important to ensure that the pipe is electrically continuous and that it is in direct contact with the earth for at least 10 feet. It's also important to bond the water pipe to the electrical system to prevent it from becoming energized in the event of a fault. Bonding is the process of connecting all non-current carrying metal parts of the electrical system together to create a low impedance path for fault currents. This includes bonding the metal enclosures of electrical equipment, metal conduits, and metal water pipes. Bonding helps to ensure that all metal parts are at the same potential, which reduces the risk of electrical shock. The NEC provides detailed requirements for bonding, including the size and type of bonding conductors and the methods of connection. It's important to follow these requirements carefully to ensure that the bonding system is effective. Regular inspections and maintenance are essential for ensuring the continued effectiveness of the grounding and bonding systems. This includes checking the tightness of connections, inspecting for corrosion, and testing the resistance of the grounding electrodes. Any problem should be corrected promptly to prevent potential safety hazards. In summary, grounding and bonding are critical aspects of electrical safety. By following the requirements of the NEC and taking appropriate precautions, it's possible to minimize the risk of electrical shock and fire. When dealing with existing installations, it's essential to assess the existing grounding system, identify any deficiencies, and correct them promptly. Collaboration with the power company and consultation with qualified electrical professionals are key to finding solutions that meet all requirements and prioritize safety. Finally, it's crucial to stay informed about the latest changes to the NEC and to adapt practices accordingly. The NEC is updated every 3 years, and it's important to be aware of any new requirements or changes that may affect electrical installations. By staying informed and following best practices, electrical systems can be made safer and more reliable. Also keep in mind that the impedance of the grounding electrode conductor plays a significant role in the overall effectiveness of the grounding system. The lower the impedance, the better the grounding system will perform in clearing fault currents. Therefore, it's important to use grounding electrode conductors that are properly sized and installed to minimize impedance. The length of the grounding electrode conductor should be kept as short as possible, and sharp bends should be avoided. Sharp bends can increase the impedance of the conductor and reduce its effectiveness. The material of the grounding electrode conductor also affects its impedance. Copper is a better conductor than aluminum, so it's generally preferred for grounding electrode conductors. However, aluminum conductors can be used if they are properly sized and installed. When connecting the grounding electrode conductor to the grounding electrode, it's important to use a connector that is listed for the purpose and that is compatible with the materials of the conductor and the electrode. The connector should be installed tightly to ensure a good electrical connection. The resistance of the grounding electrode is another important factor to consider. The lower the resistance, the better the grounding electrode will perform in dissipating fault currents into the earth. The NEC specifies a maximum resistance of 25 ohms for grounding electrodes used for services. If the resistance exceeds 25 ohms, a supplemental grounding electrode is required. The resistance of the grounding electrode can be measured using a ground resistance meter. This meter injects a small current into the earth and measures the voltage drop to determine the resistance. The measurement should be taken under dry conditions to ensure accurate results. Soil conditions can significantly affect the resistance of the grounding electrode. Sandy soil typically has a higher resistance than clay soil. The moisture content of the soil also affects its resistance. Dry soil has a higher resistance than wet soil. Therefore, it's important to consider the soil conditions when selecting the location for the grounding electrode. In areas with high soil resistivity, it may be necessary to use multiple grounding electrodes to achieve the required resistance. The grounding electrodes should be spaced at least twice the length of the electrode apart to minimize interference. The NEC also permits the use of concrete-encased electrodes, also known as UFA grounds. These electrodes consist of a length of bare copper conductor encased in concrete. Concrete-encased electrodes typically have a very low resistance and are often used in new construction. In addition to the grounding electrode conductor, the equipment grounding conductor also plays a critical role in electrical safety. The equipment grounding conductor provides a path for fault currents to return to the source from the non-current carrying metal parts of electrical equipment. Equipment grounding conductor should be sized according to Table 250.122 of the NEC, based on the size of the overcurrent protection device. The equipment grounding conductor should be run with the circuit conductors and should be connected to the equipment grounding terminal in the electrical equipment. The equipment grounding terminal should be bonded to the metal enclosure of the equipment. In summary, the grounding system is a complex and interconnected network of conductors and electrodes that work together to ensure electrical safety. By understanding the principles of grounding and following the requirements of the NEC, electrical systems can be made safer and more reliable. Regular inspections and maintenance are essential for ensuring the continued effectiveness of the grounding system. When in doubt, consult with a qualified electrician or electrical engineer to ensure that the grounding system is properly designed and installed.